everybody. Today we are going to see a program in assembly language. So this is an addition program to add 2 and 3. So we start with this hash program to add 2 and 3. Dot text main colon $8 $0 hash put 2's complement 2 into register 8 or $9 0 OX3 hash put 2's complement 3 into register 9 add u $10 $8 $9 hash add registers 8 and 9 put result in register 10 hash end of file. So this is the particular program code which we have written for adding 2 and 3. Now we'll have the explanation for this program code so that you can understand it very easily. So this character hash with which the program actually being returned, this is the start of it, right? So it is a comment actually. So everything on the line from hash to the right is actually ignored. That means it is not executable by the machine. So it is for the user purpose or the programmer's understanding as well as for the documentation purpose. Now the next one is dot text. So this is an assembler directive. This tells the assembler that the assembly program starts only after this. So this is a label or an identifier or a tag. So this tags the first location of the program code in the memory from which the program actually starts. So each of the three lines following this main colon or the statements in the assembly language, so they would be only assembled or converted into machine instructions. That means the object code. So we start with this first instruction and we'll see what it actually does. So the first instruction is $8, $0, OX2. So we all very well know that this is an assembly language statement or an instruction. So this OR indicates OR function with the immediate data. So that OR along with this I that is given here is ORI. So this is coming under immediate addressing. That means I type instruction. So the data is available in the instruction itself as an operand. We know that this OR is an opcode. It tells what to do to the assembler, what to do to the processor. Then this $8 indicates register 8. This is one of the GPR register, general purpose register available inside the CPU. So this will now act as the destination register. So the results will be saved after execution of this instruction. This $0 indicates register 0. So this is a special kind of register. That means this or register 0 that contains always 0 value as constant. Then OX2, this OX symbol indicates a hexadecimal value. So we have given a hexadecimal data. So it is hexadecimal 2. This is an immediate data 2. Now we move on to the explanation for the second instruction. It is ORI $9 $0, OX3. So already we know that this ORI, this is an assembly language instruction or a statement, and it is executable. This is executable by the processor, and this ORI indicates it is an OR function with the immediate data. That I is indicated here. So it is an I type instruction, and this is the opcode. That means from while seeing this processor identifies that OR function is to be done. So this is the opcode, and what data is available in the instruction itself will act as an operand. Then $9 that indicates register 9, that is the destination register for us where the results are stored or the saved. And $0, as I have already told you, this OR not register contains 0 value as constant always. And this 0x3, that means this is the hexadecimal value 3 which is available in the instruction itself. So this 3 will be stored in $9. So this is our third instruction, add you $10, $8, $9. So this is an assembly language instruction, and this add you instruction tells you to add the data from $8 and $9 and save it to $10. So we know that this $10 is the register 10. This is the destination register where the results will be stored after the execution of this instruction. And this $8 contains the data OX 0x2, which is the first operand, and $9, that is the register 9, that contains the data OX 0x3, that is your second operand. And this add u, within the add u, in add u we have the u, right, that represents unsigned number, as well as it ignores overflow, or the trap will not be activated. Then we have the final one, right, that is the hash end of file. This is the comment to know for us that the program is over. Now we'll see the execution of the program, how actually or what is happening inside the processor. So during the first instruction execution, that is the ORI $8 0x2, which is the immediate data. 0x2 is the immediate data. So what is the corresponding object file value or the binary code or the machine code? It is 0000 0000 0000 So it consists of only 16-bit value, which is a 2's complement value. So zero padding will be done on the left side to make the data 32 bits, because MIPS 32-bit processor we are using, right? So the modified data is like this. And then we have this $0. So what's the purpose of using $0 or 0, right? That is register 0, right? So register 0 always contains 0 value. So all the 32 bits will be having 0 value inside this or not register. Because of bitwise ORing, that is ORI instruction, ORing of this data and yes, that is $0, that means register 0 will happen. So this is your 0x2, and this is the content of or 0 register. We are going to do the bitwise ORing because of this ORI instruction. Okay. So how it will be performed? This 0 and this 0 will be ORed. The result is 0. This 1 and this 0 will be ORed. So you get the result as 1. And then the 0, 0, 0. 0, 0, 0. We know how the OR operation performs, right? 0, 0 means you will get a 0. 1, 0 means you will get a 1. If you have 0 1, again you will get a 1, and for 1 1 you will get a 1. Okay, that is the combination, or the truth table we very well know. So this is the result of the operation, and this result will be moved to $8 or register 8. So overall this instruction performs the function of moving the immediate data 0x2 into the 8th register. That's it. Now we move on to the second instruction execution. So the immediate data available in this instruction is 0x3, that is the hexadecimal 3 value. So its equivalent value in binary or the object code is 16-bit value, and it is a 3. So at the end, the last we have or LSB bits are 1 1, right? But for processing or execution, we need to have it as a 32-bit. Okay, automatically the 0 padding will be done here because of this ORI instruction. So here you will be having this 32-bit value for this data, right? And we have this $0 or not register. So these two bits values are actually ORed. So this or not content is taken, twice ORing done between these two, that means data and the $0, register 0, and you get the result. And this result will be moved on to S9, which is your destination register in the case of second instruction. So during the execution of this third instruction, that is add you $10, $9, $8, what will happen? We already know that this S8, $8 contains this 0x2, that is the first data. Then register 9 contains the second data, that is 0x3. And these two will be added together. So you'll get the value 0x5 into this 10th register or 10. So this performs the function of adding the immediate data 0x2 and 0x3, and save it into the register $10. So we got the answer here, right? So this is the function of our program. Thank you. Hope you have understood.